Hello, I'm Sophie Rovner from the American Chemical Society. Welcome to this news briefing from ACS Spring 2021. We're joined today by Dr. Chris Schunard from Florida Institute of Technology. He's developing a new detection method that could make doping by athletes tougher to hide. Dr. Schunard.
Thank you for the introduction, Sophie, and thank you to the American Chemical Society for allowing me to present on the research that's going on in our group right now. The focus for our group is looking at new novel methods for the fight against anti-doping. And so we all know how doping works. Athletes use these illegal substances in order to attempt to get some kind of unfair advantage in sport. And the way that these are most commonly analyzed, especially in the case of anabolic steroids, which are the most common class of abused performance-enhancing drugs, is by taking an athlete urine sample. Now, most commonly, these athlete urine samples then undergo a series of preparatory steps before being analyzed by some combination of gas or liquid chromatography with tandem mass spectrometry. And what our group has attempted to do is integrate a new type of technology, which is ion mobility spectrometry, into that chromatography and mass spectrometry pipeline. Now, where chromatography helps to separate various analytes like anabolic steroids based on differences in their chemistry, and mass spectrometry attempts to identify the molecular mass of these compounds, ion mobility spectrometry is a structure-based technique that allows us to tell minor differences, such as constitutional isomers and stereoisomers, that may be seen in these kinds of complex samples. And so you can see here a simple instrument schematic of the type of platform that we use here in our lab, as well as an overview of what happens in ion mobility spectrometry. Herein, ions move through a drift tube where they undergo collisions with a gas, and under the influence of an electric field, they're actually separated based on differences in their size, shape, and charge. Now, the shape is especially important here because in the case of mass spectrometry, we're often not able to identify compounds that are called isomers. These are compounds that have the exact same molecular weight, the exact same molecular formula, but the way that these atoms are arranged in a given molecule is different. And so mass spectrometry will give us the exact same answer, whereas ion mobility offers some promise in being able to separate those, and it does so on a very rapid timescale. And therefore, we can get what's shown here in the middle. It's actually a multidimensional separation technique called liquid chromatography, ion mobility, mass spectrometry, or LCIMMS, that allows us to get 3 different dimensions of information in a very short time frame. Next slide. And so what you see here in the top left is examples of several different WADA-prohibited anabolic steroids. That's the World Anti-Doping Agency. And all 4 of these compounds have the exact same chemical formula, the exact same molecular weight. And if you look at them actually quite quickly on the screen, you'd think that they don't show much difference. But some very minor structural differences, including the placement of carbon-carbon double bonds and the stereochemistry of hydroxyl groups, gives rise to very minor differences in their ion mobility that allows us to separate them. And since 2017, my group has been funded by an organization called the Partnership for Clean Competition, which allows us to develop these new ion mobility mass spectrometry techniques to separate common anabolic steroids, isomers, such as testosterone and dehydroepiandrosterone. Furthermore, we've now started to incorporate computational modeling and machine learning approaches that allow us to better determine the structure of these in silico. And last but not least, the focus of a lot of the research over the last year in our group has looked at the ability to use very inexpensive and very fast UV catalyzed reactions to further chemically modify these steroids, thereby improving our ability to resolve those. And a couple of the major methods we've focused on have been the 2 seen at the bottom: ozonolysis, where we expose these samples to gas or solution phase ozone, therefore rupturing one of the carbon-carbon double bonds located in the molecule, and the Paterno-Bucchi reaction, where we take a radical acetone and actually interact it with this carbon-carbon double bond to create an oxetane. And both of these have shown very promising results in the ability to further resolve our separation of anabolic steroids as prohibited by WADA.
All right, thank you very much. At this point, I'd like to ask if there are any questions from viewers. And if so, please state your name and affiliation in the chat window when you ask your question. While we wait for questions from viewers, I'll ask the following. So what are some common steroids that athletes use as dopants? And how many are on the World Anti-Doping Agency's banned substances list?
So every year, the World Anti-Doping Agency publishes a document called its prohibited list that goes through several different classes and several methods of prohibited anti-doping compounds in their associated administrative pathways. The first class is anabolic agents, and that includes all of the anabolic androgenic steroids that we study. And there are a little over 60 of these compounds on the list. This list is updated every year, and there are often changes to the composition of that list, whether it's substances that are added or removed, new methods that have been identified. And you'll certainly recognize a lot of the names of some of the common steroids that are abused, those especially endogenous compounds that we make naturally, like testosterone and epitestosterone that I'm sure you've read about in the news, as well as about 60 other compounds that are prohibited.
How do steroids improve athletic performance?
So what we refer to these steroids are called anabolic androgenic steroids, and that's a two-part name. The anabolic portion is to signify that they help to grow muscle mass. And of course, in any performance activity, any sport where more muscle mass and more is advantageous, that's where anabolic steroids can come in, and that they help to really build up the muscle mass of athletes. The androgenic portion of anabolic androgenic steroids has to do with the male sex characteristics, which also generally will improve performance and also lead to some also other side effects of taking the actual drugs.
Why do we need new assays for doping?
Well, that's a great question. And in the analytical chemistry world, not just in anti-doping alone, we are constantly trying to develop new techniques that improve upon any of the major figures of merit that we look at. These are things like sensitivity and limits of detection, or the ability to more accurately detect minor differences in concentration, and also to look at much lower concentrations of substances. We also look at what we call selectivity, which has to do with the ability to resolve compounds that have very or structural features. We also look at things like size and speed, as well as things like cost. And improving upon any of these is really what those of us in the instrumental analytical community have devoted our life's work to. And so in developing new techniques for the anti-doping community, we really could be focusing on any of these. Sensitivity is, of course, a major aspect that we can improve upon, because unlike a lot of other compounds that we'll see in biological samples, the steroids that we focus on are inherently at very low concentrations. So we need we have great sensitivity already, but we can always improve upon that. My group's focus has really been on the selectivity portion, which is to say that we need better methods to differentiate between compounds that look very, very similar from a chemical structure standpoint. A lot of the methods that we have right now are targeted towards those compounds on the WADA prohibited list. And so we are working on what I would consider the next generation of techniques to improve upon the selectivity figure of merit.
All right, and I don't think you've addressed this specifically yet, but in what ways do natural steroids differ from synthetic ones? And how does your assay distinguish between them?
Sure. So when we think about analyzing for doping agents with anabolic steroids, we typically put them into two major classes. The first is going to be what we call endogenous steroids. Those are the steroids that we actually make naturally in the human body. Of course, to various degrees, depending on a number of things, athletic performance, age, diet, and gender, of course. These include things like the aforementioned testosterone and epitestosterone. The other class of compounds is what we consider exogenous. These are those that the body does not make naturally. And so in some ways, they are easier to identify because presence of those at any concentration does constitute a doping violation. Now, with endogenous substances, we can look at various pathways where, assuming an athlete naturally has an increased abundance of, for example, testosterone, we could see that various precursors as well as products of testosterone breakdown would also go up in concentration proportionally to an increase in testosterone itself. If we don't see those kinds of changes, that can potentially be an indication of something that's been done illicitly. And we can also use a technique that's called isotope ratio mass spectrometry. This allows us to actually look at differences in carbon-12 and carbon-13 ratio. And this comes back to the root of your question: what are some of the differences between naturally occurring and synthetic steroids? We can actually show that the ratio between carbon-12 and carbon-13 in compounds like testosterone is different for that's made by human sources and that's derived from other things such as soy-based sources that are commonly used in the synthetic process.
All right, so how does reacting steroids with ozone or acetone help differentiate isomers?
And this is really where the basis for our research comes in. The combination of chromatography with ion mobility and mass spectrometry is a very powerful technique, and one that's really emerged over the last decade across not just anti-doping, but across all of the biomedical sciences as a way that can be better used to study things ranging from protein structure to the concentration of new biomarkers in biological samples. Where our methods come in is that, A, we want to get even more structural information. And we're already moving from a world where liquid chromatography mass spectrometry is the gold standard for so many analytical assays, especially in the clinical lab, to a world where maybe over the next few years to 5 years, we might be seeing the routine implementation of ion mobility spectrometry into some of those routine clinical assays. Well, we always want more information. And so we say, how can we get more information, but without really sacrificing much in terms of speed or cost? And so methods that we've developed use a very inexpensive UV source, a UV lamp, much like what you would see in wastewater treatment facilities, but on a much smaller scale, to form these chemical reactions using either ozone that can easily be created in solution, or using acetone that can be radicalized using this UV radiation. We form these new products of various steroid isomers, and based on these minor chemical changes, we actually create significant differences in their new ion mobility. And this is what most of the work that we've done and published has shown, that these minor changes will actually increase the resolution significantly.
How long does it take to analyze a urine sample with ion mobility spectrometry?
So one of the major advantages to mass spectrometry-based analysis in general is the speed of analysis, or what we would consider the throughput. How many samples can we analyze in a given amount of time? Now, most of these are coupled to chromatographic methods, which are going to run anywhere from a few minutes to a few hours per sample. But the ion mobility portion of this doesn't add much time to the analysis. And in fact, it actually couples very well right in between the time frames that we see for chromatography and mass spectrometry. And so to put that into perspective, with time of flight mass spectrometry, which is most commonly what we couple to ion mobility, we can acquire a full mass spectrum in about 162 microseconds. Ion mobility then allows us to separate all of the compounds in our sample on the order of about 60 milliseconds. So we can get roughly 16 full ion mobility spectra per second. And so those two couple very well together and can operate on a chromatographic time scale as well. So the throughput of our technique doesn't differ at all from conventional methods, being liquid chromatography with mass spectrometry. In fact, it actually offers us the opportunity to potentially reduce our chromatography time, potentially by as much as an order of magnitude, so that we focus less on separating these compounds with chromatography and more focus on the ability to resolve them using ion mobility.
All right, you've shown that your technique can detect nearly half of the steroids on WADA's list. What about the other half? Are those experiments in progress?
Those experiments are in progress. And from a purely chemistry standpoint, we have no reason to believe that the method that we've developed and shown to be effective for the combination of steroids already analyzed, there's no reason that those methods shouldn't work for the rest of the compounds on the list. It is just a matter of time and our due diligence to make sure that we can perform these reactions and especially do so at a high efficiency. So those reactions are currently underway. We expect to be able to publish those results hopefully during this upcoming summer, in which you'll see nearly all, if not all, of the compounds on the water prohibited list.
How do the computational modeling and machine learning techniques predict future illicit steroids? Do they work by modifying the structure of existing steroids?
So computational modeling is a tremendously powerful complementary technique to everything that we do experimentally in the lab. As the computational power that we have available to us, not just on our computers, but even on our cell phones, has grown exponentially over the last decade, it's really opened up a new avenue for us to think about the way that we do chemistry on the benchtop and in our instruments. And so since my time at the University of Florida, we've been coupling with a few different physical chemistry groups. Most recently, my colleague, Dr. Roberto Peverati here at the Florida Institute of Technology, who's very well known in the field of computational modeling. And what they allow us to do is take a much more widespread approach to the anti-doping work that we do. When we analyze these compounds, we are inherently limited by what we have access to physically. What standards can we get for various illicit compounds? What is our ability to actually get athlete urine samples? A lot of these. However, on the computational side of things, you might say that we have a theoretically infinite ability to modify steroids on paper and then in silico and look at what their resulting characteristics will be. So a lot of the time that we've spent is saying, can we take what we see experimentally, our empirical results being not just chromatography and mass spectrometry, but also our ion mobility structure, which gives us a property that we call collision cross-section, and can we do computational modeling to match those experimental results? Now, our group, as well as numerous other groups in the ion mobility community, have shown that we can do this quite reproducibly. What we are now doing is attempting to take these approaches, both computational modeling as well as a much larger machine learning approach, in hopes that we can take a theoretically infinite number of novel steroids that we've never actually seen and predict their characteristics so that if we were to actually detect one of these experimentally, we would be able to identify them almost instantly.
All right. Don't think you've addressed this one yet. What advantages does your new method offer compared to current steroid analysis methods?
So as I've kind of alluded to previously, mass spectrometry, we are able to get quite a bit of structural information that starts with molecular weight based on exact mass and can even give us some structural characteristics based on tandem mass spectrometry fragmentation patterns. Chromatography gives us some more gross characteristics, especially based on things like differences. Where ion mobility comes in is that it gives us a much purer structure-based technique where we can actually, in a very rapid time frame, differentiate minor structural differences, including some of the ones that I previously showed on my slides, changes in the position of carbon-carbon double bonds, differences between hydroxyl groups versus ketones, the stereochemistry of those, as well as a number of others. So what it really gives us is more. As analytical chemists, we always want more structural information, and that's what coupling of ion mobility with chromatography and mass spec gives us.
Right. Do you think the high cost of mobility instruments will limit the widespread use of your technique?
Well, the short answer is that anytime that we introduce a new analytical technique, we are looking to improve upon one or many of the figures of merit that I've explained. Cost tends to be something that comes a little bit later on, and this has been seen in a number of different fields, including the clinical field, when we move from what decades ago was largely based on things like immunoassays that were very inexpensive and simple to do, but lacked the sensitivity and the selectivity that we really needed to inform physician decisions, for example. And slowly but surely, the mass spectrometry community was able to convince clinical chemists that mass spectrometry was the way to go with those. Now, certainly there does involve an initial investment of actually purchasing mass spectrometry instrumentation, which is not inexpensive. But the advantages that came along with that transition have been significant to the biomedical community. There is definitely going to be an initial investment cost with upgrading these types of mass spectrometry platforms to include ion mobility. But I think that a lot of the research that not just my group, but a number of groups in the ion mobility community have shown is that there is going to certainly be a benefit that will be worth that initial cost. The other thing to mention is that ion mobility has really exploded such that nearly all of the major mass spectrometry vendors these days offer their own ion mobility platforms. And as we start to see that become much more common in the field, I think that will also allow this to become more commonplace and costs to become a little bit more manageable.
When do you think your test could be used to detect doping at an actual athletic event?
That's a good question and will certainly require a lot of follow-up testing to validate our methods in terms of things like sensitivity and selectivity. One of the things that we are currently working on is the ability to actually use not only ion mobility, but as well as some of our UV catalyzed reactions to actually do these on essentially synthetic urine samples. So can we do this in the lab to show that our methods work as well, if not better, than current methods? And so there's still a lot to be done over the course of the next 6 months to a year, but we could be looking at, in say, the next 3 to 5 years, the ability to demonstrate that our sensitivity meets the requirements for such rigorous testing of very low concentration anabolic steroids.
All right, 2 last questions for you. First, what are your next steps for this research? You've touched on some of that, but
Sure. So I'd say that's kind of threefold right now. We actually just got word in the last 2 weeks that we've been funded for our next round of funding through the Partnership for Clean Competition, who's been very helpful in funding all of our work and really helping my group become independent in that manner. The 3 things that I'd say we're going to be focusing on over the next 6 months to a year is expanding our methods to a wider range of compounds, not just anabolic steroids, but also looking at a few other classes. We have a student giving a presentation, for example, on glucocorticoids this week, which are a different WADA banned class of substance, structurally similar in ways because they're also considered to be steroids, but they work in much different manners than anabolic steroids. The second is really expanding our computational methods. And again, the new funding that we've gotten is really focused on taking and expanding our list past tens and hundreds, but really to thousands and hundreds of thousands of theoretically possible steroids and figuring out what their structure will look like and what they would ultimately look like in an analytical test that we could run here in the lab. And the last thing is really taking this to what we call in the mass spec community prime time. Can we take what we do here in an academic lab and can we actually start to translate it over to what could be used in a real world setting? And that again involves validating things like the sensitivity and the selectivity of methods with real samples. And the Partnership for Clean Competition has been tremendously helpful in assisting us in doing that. So we're really excited to see what our group, especially our grad students that have been working hard for all of these presentations, to see what they can do over the next year.
all right, last question for you. What take-home message about this research do you want to leave with viewers?
The take-home message that I have here for the viewers is that a lot of the methods that we're using now, especially these UV catalyzed reactions, are not necessarily reactions that our group has invented. Actually, these are organic reactions that have been used successfully for decades. But what we're attempting to show is their wider utility in an analytical sphere. And so So these reactions have been implemented for other biomolecular classes, including lipids, but we want to show that their utility in anti-doping can be just as significant. And furthermore, I think these types of low cost and high efficiency reactions could also have an even wider benefit to other types of biomolecular classes. And so the take home message here is that we are developing low cost methods that could potentially be used in any analytical chemistry lab around the world to get more information than is currently available with our techniques today.
All right, thank you very much. The archived version of this session will soon be posted at www.acs.org/ACS Spring 2021 conferences. Please join us for the next press conference at 11 a.m. Eastern today on paleopharmaceuticals from Baltic amber that might fight drug-resistant infections. Thank you.
Thank you.